And here we have discussed that is supervised, unsupervised, self-supervised, semi-supervised, reinforcement learning, as well as transfer learning. So if we'll just make a comparison of these differences between the different type of learning, that is traditional programming, supervised learning, unsupervised learning, reinforcement learning. In case of traditional programming, there is some set of rules as well as some set of I can say data is present and we are getting the answers. In case of supervised learning, the answer and data are given and we are finding some set of rules. And in case of unsupervised learning, there is data is given and we are finding the rules. And reinforcement learning, which plays a very vital role in all kind of applications, which uses one reinforcement agent and another is called the environment. So there are two blocks are present. One is called the agent and the environment. So there is a feedback from this environment to the agent. Now, based on the feedback, the agent has to take an action in such a manner that the reward has to be maximized. So this is the all type of different type of learnings. So if we'll summarize these different machine learning concepts, they are used for various applications in day-to-day life. So here I have made a table that is this machine learning as you have discussed, that is supervised, reinforcement learning, unsupervised learning. Under this supervised learning, we are talking about the classification as well as regressions. So this classification makes the grouping of the different things into different groups or different objects into different groups. And we'll talk about more about these classifications. There are binary decision tree, Naive-Bayes classifier, neural network classifier, convolutional neural network classifier, deep belief neural network, recurrent neural network. And supervised learning also used for regression, that is the neural network as well as trees. It has many applications of this supervised learning. Name a few, that is image classification, character recognition, facial recognition, surveillance system, diagnosis of different type of diseases, etc. Regression, it is mainly used by or performed by this neural network as well as trees. This is advertising and business intelligence, that is Google Ads, weather forecasting, market forecasting, political campaignings, etc. Reinforcement learning, as I told, there is one agent and the environment is present, and there is a feedback from this environment to the agent in such a manner that feedback from this environment to the agent, and the agent will take an action by looking to the condition of the environment so that the reward is get maximized. And basically, this is used for real-time applications. Under this category, deep Q networks have been used, double Q learning, parameterized experience relay also used. So this gives rise to real-time decisions. That is a game, artificial intelligence, learning tasks, skill acquisition, personal assistance, as in case of Google or Microsoft Cortana, Apple Siri, etc., autonomous self-driving cars, etc. Unsupervised learning, that means there is no annotation is present, and this is mainly used for dimensionality reductions, clustering, density estimations. If you look into the dimensionality reductions, this stack autoencoders have been used, local linear embedding is used, auto-assistive neural network have been used, and this is mainly used for big data visualization, structural discovery, meaningful compression, etc. Clustering, where cluster the different data into different or cluster the data into groups. Here people are using convolutional neural network, deep belief network, K-means clustering, etc. And this clustering is mainly used for different type of engines, that is Amazon Web Services, Netflix, customer segmentation, targeted marketing, filtering algorithms, news feeds, etc. Density estimations. This density estimation is performed by Gaussian mixture or kernel density. If you look into the deep neural network concept, that is deep Boltzmann machine is used. Generative denoising or auto-encoders is used. In this case, this is economics, risk predictions, etc. have been used. So here I have summarized this machine learning algorithms, that is different machine learning algorithms for the different applications, and as well as which kind of network or neural network have been used for different type of applications. So if we look into this supervised learning, this is performing two tasks. One task is called the classification task, and another task is called the regression task. What is classification task? Basically, this is a task of predicting a discrete class level output for a given input. And what is regression? Regression is nothing but a problem of predicting a continuous quantity output for a given example. So whenever we are performing this classification or the regressions, the algorithm has to perform well to the unobserved inputs, not just for the data which are used for training purposes. So that means we are using certain data for the training purposes, and we are using certain data for the testing purposes. The data which have been used for the testing purposes have not seen by the training model. Then we can able to calculate the error, or we can calculate the performance of this particular model. So the ability of performing well on the unseen data is given rise to or represented by the generalization error. So there are two types of errors. Basically, we are looking into, or we are considering in case of our model. That is, one is called the training error, another is called the testing error or the generalization error. So our aim always to be, or aim should be such that the model should perform well to the unseen data or to the unobserved data. So as we have discussed this supervised learning, so there are different learning algorithms people have used. These learning algorithms have been implemented in a neuromorphic hardware. Work has to be focused on spike-based learning rules. Non-spike-based ones, that is least mean square error, perceptron. We'll talk about this least mean square error as well as perceptron in later slides. So this perceptron basically consists of a single neural network. So if you look into both least mean square error and perceptron, this behaves or work on a minimum disturbance principle. That means that corrects the error at every step by minimal change of the parameters to maximize the memory capacity. LMS is implemented in an adaptive circuit exclusively in case of filters. Perceptron is nothing but a kind of a neural network which can able to classify a linearly separable classes. We'll talk about more in detail what is that linearly separable classes and how this can be done. Non-linear network by adding a threshold function at the output of an adaptive linear combiner, that is adenine. And this doesn't guarantee low classification error for the non-linearly separable classes. So that means this perceptron has the limitation that it cannot able to separate the non-linearly separable classes. Back propagation and as well as a gradient descent have been the popular learning algorithms for the training both the shallow as well as the deep neural network in past decades. So if you look into the issues of this back propagation, it is costly both in terms of memory as well as power due to the higher precision weights. Smooth activation functions. There are many type of activation functions have been used for this machine learning concept, and we'll few of them we'll discuss about. That is tan hyperbolic, sigmoid functions, etc. Significant number of multiply as well as accumulate, that is Mach unit operations for both forward as well as backward passes. Back propagation requires a global information about the errors, as well as the weights in backward pass that are exactly symmetric with respect to the weights of the forward pass. So weight transport problem along with alternating forward and backward passes and precise floating point weights make the standard back propagation an implausible learning technique for neuromorphic architectures. So the computational complexity and optimized memory resources problems in the back propagation can be resolved by a pipeline and back propagation as well as a binary state network. What is pipelined back propagation? That network has access to the previous network states and helps delayed weight updates during the subsequent forward pass without the need of an explicit backward pass. This architecture reduces the number of memory fetches and lookups corresponding to the backward pass significantly. Reduction of redundant off-chip memory fetches reduces the power of overhead appreciably. binary state network. In case of a binary state network, the output of a neuron can be unipolar, that is 0 or 1, or bipolar, that is -1 or 1. This modification transforms the multiply and accumulate operations in the forward pass to the simply additions as well as the subtractions. Operations become synaptic operations that facilitate the neuromorphic implementations. So a requirement of the high precision floating point weights and the gradient problems is addressed by two approaches. One is called the off-chip learning, which uses high resolution weights and gradients, and consequently rounding of the weights to a lower resolution for on-chip implementation. And on-chip learning using low resolution weights in randomized rounding has been used to map high resolution gradients to low resolution discrete values. So used for this spiking timing dependent plasticity, this STDP is used for computational models. The simple doublet STDP rule that doesn't generalize well to spike train stimuli in learning experiments. It is unable to replicate biological measurements such as dominance of long-term potentiators at higher frequencies independent of spiking time differences. Spike-driven synaptic plasticity, it overcomes the limitation of STDP. STSP takes into the account of post-synaptic depolarization, that is VT, as well as the post-synaptic firing rates captured in a calcium variable, that is CT. So the synaptic weights are binary that makes easy implementation in CMOS hardware without using a non-volatile memory. The structural plasticity, that is weight plasticity, that is named as structural plasticity, change in synaptic weights helps in learning in neuromorphic systems. Network structure of adult brain undergo plasticity with new connections that are replaced by old ones. So the advantages of structural plasticity is the presence or absence of connections can be indicated by 1-bit signal and easy to store by the CMOS latches. So as we have discussed, in case of supervised learning, we are talking about two things. One is called the classification, another is called the linear regressions. Now we'll try to understand what exactly this linear regression represents. So in case of linear regression, the goal is to build a system that can take a vector x as input and predict the value of a scalar y as its output. So that means we can predict that y hat, that is the prediction, that is nothing but your W transpose into x. So what is this x? This x represents the input and y hat represents the prediction. So whenever we are predicting certain things, our aim is to that this model can able to predict correct values or can able to correct or predict the correct one. So that means y hat must be equal to this y. And what is this W? This W is representing a set of weights which determine how each feature affects the prediction process. So that means this W can take both positive value as well as the negative values. If W is positive, it increases the prediction as input feature vector increases. And if W is negative, that means it increases the prediction as the input feature vector decreases. So we are calculating y hat is equal to WTX. So that means y hat must be equal to y. So this difference between y hat and y must be equal to very, very small, that is equal to 0. So x is the, or that means we can say that the prediction depends upon this weights that is equal to W. So as the will increase as the input feature vector increases and W decreases. And if we are making this W to be 0, there is a no effect in the prediction. Am I audible? Yes, am I audible to all of you? Yeah. So in this case, our aim is to make this prediction that is equal to y hat must be equal to y. So that means how we can make this, how we can do or achieve this situation. So for that reason, we have to calculate the performance of the model by the help of a mean square error. And how we can able to calculate this mean square error? This mean square error can be computed as 1 upon n, that is the total number of samples, summation I, that is y hat test minus y test whole square. So y predicted test, that is nothing but the prediction, and y is nothing but the output, exact output. So now this value to be equal to 0, and this value will be 0 if and only if y predicted, or that is y prediction test must be y test. And how we can achieve this, or how, on what condition we can able to achieve this? So this depends upon these weights. So that means if we will adjust these weights in such a manner that this y prediction must be equal to y, so improve the weight minimizes the error on the training set. So how we can find this weights? So for that reason we have to calculate the gradient of this mean square error with respect to w, or that is the weights, and we can go for the simplification, and we can get this value of w, that is nothing but the optimum value of w, where this y prediction must be equal to y. So this represents the simple learning algorithm. This simple learning algorithm says for an optimum value of w, this y prediction is becoming equal to y, and so that we can get this error to be very, very less, that is equal to, or small, that is equal to 0. So here I have taken one of the example by considering 10 data points. If we look into these 10 data points, these 10 data points are presented here, and it contains only one feature. So W has only a single parameter to learn. So the left-hand figure represent the linear regression learns W1, and the line becomes as close as possible to pass through all the points. So this, if we look into the line, that is the blue line, it can able to pass through all the data points. What does it mean? It means that the sum of the distances from all the data points to this line is equal to minimum. So if we look into the right-hand side of the figure, that is the optimization of W, which represent that how this MAC is basically varying with respect to the different value of W. So this y-axis is represented the MAC, mean square error, and this x-axis is representing the value of W. So for different value of W, this MAC is changing. So at the optimum value of W, this MAC is found to be minimum. So at this point, this MAC is to be minimum. So what does it mean? That means this is called the optimum value of, that means y prediction will become equal to y. So in case of linear regression, we have represented this y is equal to WTX. That is, W is nothing but the weights, and x is nothing but the input, and y is the, we can say, the prediction or the output. So linear regression is often used to refer more slightly sophisticated model by adding one more parameter to this, and that is known as the bias term. And this bias plays a very vital role in case of this classification or the linear regression that we'll discuss later on. So this bias is an extra entity or entry which is set to 1. So linear regression we have discussed here because it is very, very simple, and it is a limited learning algorithms. And there are exponential regressions, logarithmic, etc. are also present. Next, we'll talk about this capacity overfitting as well as underfitting. As we have discussed, that these deep neural network models are very, very data hungry, and during the training phase we have to find the value of W so that this y prediction must be equal to y. That means the error is to be very, very low, that is equal to 0. That means y prediction is equal to y, it is equal to 0. So here we are getting two type of error. One is called the training error, the error which is occurred during the training process, and another is called the test error, that is called the generalization error, which is occurred during the testing process or the test error. So this training error as well as the test error has to be minimized. That means what is our what our model basically demands, that is the generalization error has to be minimized. What is generalization? This generalization represents the ability of a model to perform well on the previously unobserved input. That means we have to give some unobserved input to the model, and this model can able to classify or able to find or segregate or perform well on the perform well. So optimization basically provides a generalization error that is known as the test error and which has to be minimized. So this generalization error tells about the test error and this test error has to be minimized. But regression train the model by minimizing the training error. So our interest is on the test error, or that is the generalization error. So what is our aim? Our aim or our motive is to reduce the training error as well as reduce the test error. So how we can achieve this? This can be achieved by a data generating process, as already we have discussed. So this deep learning requires a huge amount of data. So this data generating process is IID, that is independent as well as identically distributed. So each data set is independent from each other, and that the train set and the test set are identically distributed. So the factors that determining the performance of this machine learning algorithm are nothing but the training error, and another is called the test error. So training error should be very, very small, as well as the test error should be very, very small. And the gap between the training error as well as test error to be very, very small. So this leads to the different conditions in case of deep learning, that is called the underfitting, overfitting, as well as capacity. So what is underfitting condition? This underfitting condition model not able to obtain sufficiently low error at the training set. So the model cannot able to provide the low error during the train or during the training phase or the training process. That is known as the underfitting conditions. What is overfitting condition? The overfitting condition represent the gap between the training and test error is large. That means we can say that the model can able to perform well on the training data, but the model doesn't perform well on the test data. That means the test error reduces here, but the training error is low. So the gap between both of them is increases. So this will lead to the overfitting condition. Next is the capacity. This capacity represents the ability of a model to fit a wide variety of functions. So what this capacity represent? The capacity makes the model to overfit, or it will make the model to the underfit conditions. So here I have represented the capacity, overfitting as well as underfitting by the help of three graphs. So what the model of a low capacity? So if the model is having a low capacity, it struggles to fit the training set. So that means it cannot able to pass through all the data points. So here I have shown one example that is called a case of the underfitting condition. Here are certain points. So in case of underfitting that is called low capacity, the model cannot able to fit all the data, or the straight line cannot able to pass through all the data points. So model of low capacity struggle to fit the training set. Model with high capacity will overfit by memorizing the property of the training set that will not serve well on the test set. So in case of high capacity, the model can memorize the training samples. As the model can memorize the training samples, it will perform well on the training data, but it will not perform well on the test data. So that is called the overfitting condition. So this is the overfitting condition where the model can perform well on the training data, but in case of testing data, this will not perform well. So this is the model with high capacity will overfit by memorizing the property of the training set that will not serve well on the test set. Control the capacity by a hypothesis space. So what is appropriate capacity? In appropriate capacity, the model has a low training error as well as the model has the low test error. That means it can able to fit all the data points properly. So here, how to quantify the capacity? Basically, Vapnik-Chevornsk dimension, or popularly known as the VC dimension, is used for quantifying the capacity. So this capacity measures a binary, or measures the capacity of a binary classifiers. So here one diagram I have shown which represent the capacity versus error plot. The capacity is taken along the x-axis and the error is taken along the y-axis. So there are two color graphs are present. One is called the dotted blue line, which is representing the training error, and another is the solid green line, which is representing the generalization error. If we look into the extreme left-hand side, we can see that this training error is not sufficiently low, and this region is called the underfitting zone. And if we look into the extremely right, we can see that the gap between the training error, that is the blue line, and the generalization error, that is nothing but the solid green line, is too high. That means the gap between them is very, very high. And this region is called the overfitting region. And if we look into this red line, that is nothing but the optimal capacity. In optimal capacity, this error due to the training phase is very, very low, as well as the testing phase is also very, very low, and the gap between them is also very small. So this also about the capacity overfitting as well as the underfitting conditions. So as we have discussed, what is this machine learning, and we are talking about this artificial intelligence is incorporated. So if we look into this artificial intelligence, basically this encompasses this machine learning as well as deep learning, and it was not a very new concept. It was developed a very long back, that is 1950s. And this makes the computers made to think like the human beings, and this is possible due to this neural network. So the effort to automate the intellectual task normally by performing how the humans are basically performing, that is nothing but the artificial intelligence. So DL is evolved from this artificial neural network. So what is this neural network? This neural network is nothing but the interconnection of networks or interconnection of these neurons as it is found in our human brain. So that is represented as interconnected networks of a processing unit called artificial neurons, and that can loosely mimic the actions that is found in the human brain. So here I have taken this representation how this is connected in case of our human brain. If you look into our human brain, humans are basically born with 100 billion of neurons, and neuron may connected many other neurons. So the signals basically move via electrochemical signals, and the synapse release a chemical transmitter, the sum of which can cause a threshold to be reached and causing a neuron to fire or to respond. So synapse can be inhibitory or excitatory. So now there are certain dendrites. There is a nucleus, that is the cell body, and this is the axons. Again, these are called the axon terminals. If you look into these dendrites, these are nothing but the input points. So these input points are fed into the cell body, and this cell body, they are all summed up. And if it is crossing a threshold, that means it will fire. If it is below the threshold, it will not fire. So this is nothing but the structure of a biological as well as the artificial neuron. So if we represent the electrical representation or electrical equivalent of this neural network, this will look like something like this, in which there are certain number of input nodes are present, which is represented by x0, x1, x2 up to xn. So these signals are passed to the neurons. They are multiplied with a weight. So these are called the weights. These weights are represented by W0, W1, W2 up to Wn. So each input that is associated with a weight. So here I can talk about this W0 is equal to the bias torque. So now this multiplication of this input with the weights get summed up at this cell body, or that is performed at the soma. So this summation is passed into a activation function. So if this summation crosses the activation function, the neuron is fire or neuron fires. If it is less than the activation function, this neuron doesn't fire. So we can represent this output of this cell body or soma, that is nothing but y is equal to wtx plus b. So where wt is representing all the weights, that is equal to w0, w1 up to wn, and x is representing all the inputs, that is equal to x0, x1 up to xn, and b is nothing but the bias. So for binary threshold, the output 1 is provided when total input exceeds the threshold, otherwise stays at 0. So if we look into the neural network, so there are major events. Major events to this neural network. How this neural network have been evolved from this artificial neural network. So the first neural network that was developed in 1943, and it is called the first neural network. So it was developed by McCloskey and Pitts, which is known as the first neural network. Many of the ideas are still used, that is just simple units to combine to give increased computational power and the idea of the threshold. So in 1949, Hopf developed the first learning rule. That is, if two neurons were active at the same time, the strength between them should be increased. So during 50s and 60s, the perceptron was developed, which amidst a great excitement. And if you look into 1969, there is a death of this neural network about nearly 15 years. So in 1990, the support vector machine was developed by Vapnik as well as Coates. And it is a very popular neural network for scaling up to large problems. So artificial neural network are renamed as this deep learning by Geoffrey Hilton and other introduced the idea of unsupervised pre-training, deep belief network, as well as the ReLU activation functions. So here tells about the evolution of this artificial neural network. So in 1943, Warren McCloskey as well as Walter Pitts developed this binary threshold neuron. So in 1957, Frank Roosevelt invented perceptron and the famous perceptron rule or the perceptron loop. 1960, Minsky and Puppet showed the limitation of the perceptron. So what are the limitations? Basically, the perceptron can able to separate the linearly separable classes, but it cannot able to separate the non-linearly separable classes. So artificial neural network community perceived these limitations applied to all the artificial neural network. There is a break in from this 1960 to 1980, and there is no research in the direction of this artificial intelligence. In 1980, Geoffrey Hilton, David Rumelhart revived this artificial neural network by inventing back propagation for training this multi-layer perceptron network. In 1990, the support vector machine was invented by Vapnik and becomes very famous for separating the non-linearly separable classes. In 2006, artificial neural network was renamed as this deep learning because of this deep belief network as well as unsupervised pre-training for neural networks introduced by Geoffrey Hilton and AI. In 2010, this ImageNet coming into picture, and 2012, Alex Krzyzewski, Ila Sutasker, and Geoffrey Hilton won this ImageNet computation using deep learning by a huge margin. Dropout regularization and ReLU activation was introduced. GPUs are used to train this model. So we'll talk about first this perceptron, which was developed or in 1943 and 57, so 1957 by Frank Roosevelt. So what is this perceptron? This perceptron is nothing but a linear binary classifier. This linear binary classifier can able to classify the linearly separable data. So here one example I have given, there are two classes are present. One is called the class which is represented by the plus sign, and another class which is represented by the negative sign. So these two classes are separated by the help of a straight line. So this is called a linearly separable class. So perceptrons can able to separate a linearly separable class by the help of a hyperplane. So in this case, the learning algorithm fetch the weight as well as the bias for the classification. So what is this AB? This AB represents the straight line or the hyperplane, which can able to separate the two classes. And this straight line can be represented by y is equal to, I can say WTX plus B. And what is this B? This B represents the distance of this line from this origin. So depending upon this bias term, we can control this position of this straight line either towards this negative group or towards the positive group, so that the two classes can be separated correctly. So bias represents the distance of the hyperplane from the origin. If I represent this W dash X dash plus B greater than 0, then it will belong to one class. If this is less than equal to 0, this will belong to the other class. So the perceptron can able to separate the linearly separable classes. So this is one example. Now we'll take one real life example of the perceptron, that is a logical OR gate. We know in case of a two input logical OR gate, there are two input and a single output. How we can able to separate the output of a two input logical OR gate? We know that this OR gate will provide an output is equal to 0 when both the inputs are 0. If one of the input is equal to 1, the output is equal to 1. So that means for 0, 1, it is 1, 1, 0, it is 1, as well as 1, 1, it is also 1. So now if I'll try to separate the output of a two input logical OR gate, that is a separation of the zeros as well as ones, which is nothing but a linearly separable classes. How it will be a linearly separable classes? Just we'll look into by the help of a diagram. So here I have taken one input x1 along the x-axis and another input x2 along the y-axis. So that means for 0, 0, the output is equal to 0 and it is represented by a black color. And rest of the combination, that is 0, 1 as well as 1, 0 and 1, 1 is give rise to the output that is equal to 1 and which is represented by a red color. So now if I want to separate the output that is equal to 1 from the 0 by the help of a straight line, I can draw a straight line. And what is this straight line? This straight line is a function of W1, W2 as well as B. What is W1? W1 is nothing but a weight and W2 is the weight and B is representing the bias that represent the distance from this origin to the straight line. So if I will consider this W1 is equal to 1.0 and W2 is equal to 1.0 and bias is equal to minus 0.5, then we can see that for 0, 0 combination, I will get the output to be negative. For rest of the combination, I will get the output to be positive. So that means if I will take a neural network which is consists of two input as well as one output, for 0, 0 combination, I will get the output to be negative, and for rest of the combination, I will get the output to be positive. So that means by using a threshold, I can able to separate the output of a two input logical OR gate. So this will nothing but how we can able to separate the outputs of a two input logical OR gate by the help of a perceptron. So the perceptron can able to separate the linearly separable classes. So this is a linearly separable classes. The same thing occurs in case of a logical AND gate. So what will happen in case of a logical AND gate? We know that the output of a logical two input logical AND gate is equal to 0 if any one of the input is equal to 0. That means for 0, 0, the output is 0. For 0, 1, 0, 1, 0 is equal to 0. And when all the inputs are 1, the output is equal to 1. If we want to separate the output of a two input logical AND gate by the help of a perceptron, then we can take x1 along this x-axis and x2 along the y-axis, and this 0, 0 combinations will give rise to 0, 0, 1 as well as 1, 0 also 0. So that are represented by a black color, and for 1, 1 combination, the output is represented by a red color. So now if we want to separate the output of a two input AND gate functions, I can able to separate by the help of a single straight line. So this straight line is depending upon the parameter that is equal to W1, W2 as well as the B, that is the bias term. So if I will consider this W1 is equal to 1.0 and W2 is equal to 1.0 and B bias that is equal to minus 1.5, then we can see that for 0, 0, 0, 1 as well as 1, 0 combination will get the output to be negative, and for 1, 1 combination, the output is to be positive. So we can represent this two input logical AND gate function by the help of this neural network in which there are two inputs are present and one output is present. So that means for 1, 1 condition, that means when all the inputs are 1, the output is positive. When one of the input is equal to 0, the output is negative. So we can able to, by the help of a threshold, we can able to separate the output of a two means we can able to classify the data which are linearly separable. So I hope everybody has understood this. Yeah. Now we can see what will happen if the case is like this, or multi-layer neural network, or take the case of the example of a two input exclusive OR gate. In case of a two input exclusive OR gate, the output is equal to 0 when both the inputs are identical, or that is 0, 0 condition, we are getting the output to be 0. For 1, 1 condition, the output is equal to 0. But rest of the condition, that is 0, 1 as well as 1, 0, the output is equal to 1, 1. If we want to represent the truth table by the help of a graphical representation, then we can see that for 0, 0, the output is equal to 0, and for 1, 1, the output is equal to 0, but rest of the combinations, that is 0, 1 as well as 1, 0, the output is not equal to 0. This is equal to 1. So if I want to separate it, separate the output of a 2-input logical OR gate, then I could not able to separate it by the help of a single straight line. I have to use 2 straight lines. So that means this is a condition of where we can say that non-linearly separable classes. So how this is the limitation of this perceptron. So what is the limitation of the perceptron? The perceptron can able to separate the linearly separable classes, that classes which can be divided by the help of a line or a hyperplane, that are called linearly separable. So most of the functions are more complex, that is they are non-linear, not linearly separable. That is one of the examples that I have given, that is exclusive OR gate. So how we can able to separate it? By the help of a neural network, or by the help of artificial neural networks. So this gives rise to the concept of a multi-layer neural network. So what this multi-layer neural network represent? That means instead of a single input and output layer, we have multiple number of hidden layers. So this is, gives rise to the condition of the machine learning, that is multi-layer neural network. So the complex multi-layer networks are needed to solve more difficult problems. That means the classes which are not linearly separable. So here we are talking about this Hopfield neural network. That is, every output node is connected to the every input node, or the radial basis function, that is RBF, which convert non-separable problem to a linearly separable problem. Or we can able to achieve this condition by the help of the activation functions that makes the output to be very or linear. So we'll talk about this, how we can able to solve this exclusive OR problem by the help of radial basis functions. So this radial basis function is a non-separable problems, or this radial basis function makes a non-linearly separable class to a linearly separable class, or I can say non-separable problems to a separable problem. So how this radial basis function can achieve this? This can be achieved by increasing the dimensionality, by using a nonlinear transformation. So there is a receptor is used, that is known as the T, and as we are moving away from the receptor, the value is basically increases or it will decreases. So what this radial basis function is doing? This radial basis function maps the input that is equal to x to phi of x. Here I am talking about a Gaussian basis function for simplicity. So phi x is equal to e to the power norm x minus t square. So that is equal to exponential of x minus t square. So what is t? T is nothing but the receptor. As we are moving away from the receptor, the value is gradually increases or decreases. Now we'll take the same example, that is 2-input exclusive OR gate. So in case of 2-input exclusive OR gate, for 0, 0, the output is equal to 0. For 1, 1, this output is equal to also 0. So rest of the combination, that is equal to 1, 0 or 0, 1, the output is equal to 1. So now how we can able to make this non-linearly separable classes to a linearly separable class by the help of a radial basis function. So in this case, for every receptor, we have to determine the p number of neighboring receptors. If we take this receptor that is equal to T1, that is equal to 0, 0, and T2 is equal to 1, 0, T3 is equal to 0, and T4 is equal to 1, 1. So then we want to find the neighboring receptor for this T1. So how many neighboring receptors are present? There are 2 neighboring receptors are present. T2 is a neighboring receptor to T1, as well as T3 is a neighboring receptor to T1. So that is equal to P is equal to 2. So if you want to calculate your standard deviation, that is equal to 1 square plus 1 square divided by 2, that is the root mean square distance, that is equal to 1. So now, when we have to compute what is your phi 1x corresponding to this receptor that is equal to T1, that is equal to 0, 0. And at that time, what is sigma 1? Sigma 1 is equal to nothing but 1. Similarly, for T2, what is it sigma 1? That is equal to 1 because all are symmetric. So I can say this is sigma 1, sigma 2, sigma 3, and sigma 4 are all 1s. So now I have to compute phi 1 for this T1 and sigma 1, phi 2 for T2 and sigma 2, phi 3 for T3 and sigma 3, and phi 4 for T4 as well as sigma 4. 0. So what is phi 1x? The phi 1x corresponding to this receptor T1 that is equal to 0, 0, and the sigma 1 that is equal to 1 can be represented as exponential of minus x minus T1 norm square divided by 2. Similarly, we can compute for phi 2 that is equal to e to the power x minus T2 norm square divided by 2. For phi 3, e to the power x minus T3 norm square divided by 2, and phi 4 that is e to the power minus x minus T4 norm square divided by 2. So now if we will represent this input as well as all the phi's by the help of a table, so that means we have 4 inputs, that is 0, 0, 0, 1, 1, 0, as well as 1, 1. So we'll compute the phi 1, phi 2, phi 3, and phi 4 for all the inputs. So that means we have computed phi 1 for all the inputs, phi 2 for all the inputs, phi 3 for all, as well as phi 4 for all. So if I will consider this W for this phi 1 that is equal to minus 1.0, and phi 2 is equal to plus 1.0, and phi 3 plus 1.0, and phi 4 minus 1.0, and we will calculate the summation I is equal to 1 to 4 wi phi I. We can see that for 0, 0 input the output is to be negative, and for 1, 1 input the output to be negative, and for rest of the combination that is equal to 0 and 1, 0 the output is to be positive. So that means by the help of a simple threshold I can able to separate the output of a 2-input exclusive OR gate. So that means for 0, 0, I am getting the output to be negative. For 1, 1, I am getting the output to be negative, and for rest of the combination, the output to be positive. So by the help of a threshold, I can able to separate the output of a 2-input exclusive OR gate. So what this radial basis function is doing? This radial basis function is converting the 2D feature vector to a 4D feature vector. So that means we can say that there is a hidden layer computed for this radial basis functions. So how we can represent graphically? So there are 2 inputs. One is called the x1 input, another is called the x2 input. So there are this 2 input or 2D feature vector now it's converted into a 4D feature vector. Here basically we are making into a higher dimension. So and we are getting the final output to be either positive or to be negative. So depending upon the threshold, we can able to separate the output of a 2-input exclusive OR gate. So what we understood from here? So this mapping, that means this function that is called radial basis function introduces another layer into the neural network, and this will give rise to a multi-layer network, or that is giving rise to the more number of layers, which basically separates the non-linearly separable classes to a linearly separable classes. So this same operation can be achieved by the help of these activation functions. People have used many kind of activation functions like a linear, bilinear threshold, sigmoid activation function, tan hyperbolic x, softmax, rectified linear unit, etc. So what is this linear activation function? So this linear activation function in which the inputs are represented by x1 to up to xn, and weights are represented by w1 to wn, and we are representing the output that is equal to I is equal to w1 x1 plus w2 x2 up to wn xn plus b. So this can be represented by these graphical representations. Next activation function is called the binary threshold. So if we are achieving this threshold, this output will become positive, and if it is less than the threshold, it will become equal to 0. Or neuron is activated if the net input of the neuron is exceed a specified threshold. So that means Z, we can say the WTX plus B, and if Z is greater than certain threshold, we are making this is equal to 1, and otherwise it will be equal to 0. So K is the threshold beyond which the neuron is get activated. Next is the sigmoid function, which can be represented by y is equal to 1 upon 1 e to the power minus g, and where g is equal to WTX plus b. If this e to the power minus g will tend towards 0 when y tending towards 1, and this will tend towards infinite when y is tending towards 0. So that is e to the power minus j tending towards 1 when y is equal to tending towards is equal to half. And this sigmoid function is a very smooth function and gives a nice continuous derivative, and its range is from 0 to 1. In the hidden layer, it introduces non-linearity, that is model learns some complex features. Tan hyperbolic x can be represented by e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z, and where z is equal to nothing but WTX plus b, and y is equal to tan hyperbolic z. And this z will become positive That means e to the power minus z tends towards 0 and y tending that is equal to y tends towards 1. So you can have a look into that. So range is from -1 to 1, and it saturates around the output is equal to 0. The most important activation function that is used in case of deep learning, that is known as the rectified linear unit, or popularly known as the ReLU activation function. This rectified linear unit or ReLU activation function are revolutionized that's deep learning concept. In this case, the output is equal to input of the neuron if the overall input is greater than 0. In this case, the output is equal to the input, and this overall input is greater than 0. It has a constant gradient for the positive input and a 0 gradient for this elsewhere. So there are two versions of this rectified linear unit. One is called the parametric ReLU, another is called the leaky ReLU. So if you look into the input-output relationship of this parametric ReLU, this can be represented as y is equal to maximum for 0, z plus beta mean 0, z. So beta is equal to -1, that is equal to y is equal to z. So absolute value of ReLU activation, and y is equal to 1 for z is less than equal to 0, beta z plus 1, z is greater than 0. And in this case, beta is considered to be 0.01. Similarly, there is a exponential linear unit is also present. Next important activation function is softmax activation function, which basically perform the work of classification in case of deep learning. So what is this softmax activation function? This softmax activation function finds the probability of the ith class for a given input vector. So how we can able to represent it? So that means we have a sort of input vectors, and we can find the probability of the ith class for a particular input vector, or mathematically we can represent as probability of yi is equal to 1 for a given input that is equal to x, and that can be represented as exponential of wi transpose x plus bi, and summation j is equal to 1 to k e to the power wzt x plus bj. So for two classes, the softmax function can be represented as probability of y1 is equal to 1 for a given input x. That will be represented as exponential of w1 transpose x plus b1, and divided by e to the power w1 transpose x plus b1 plus e to the power w2 transpose x plus b2. So this by simplification we can able to get this. So this softmax finds the probability of the ith class. That means whether it will belong to class 1 or class 2 in case of a two class problem. Here there are two sets of weights that is equal to w1 and w2, and loss function is called the cross entropy loss function, which can be represented as c is equal to I is equal to 1 to k minus yi log probability of y I is equal to 1 for a given input vector that is equal to x. So this is the activation function for the softmax. So I hope this is a nice time to stop here and take a break for 10 minutes. Then we can have a discussion about the further slides. We can have a discussion around 10 minutes, 12 o'clock we can start.